Hello guys, and welcome back to another video. Today I want to show you this library that I made for Java called Java Expression Parser, which, you guessed it, parses expressions. In order to use it, it's very simple. You just have to instantiate a new expression object and then call expression.evaluate. And this expression supports all four basic operations and parentheses, as well as order of operations. So, for example, we can do 1 plus 1, which, when ran, will give us 2. But if we do 1 times 2, this should give us 3, using order of operations, which it does. But if we want to have it equal 4, we can add some parentheses, which gives us 4. We can also add inner parentheses, 0.5 times 2, which will also give us 4. And you can even inner the parentheses. And you can keep going as deep as you would want. So the way this thing works is the actual expression class is quite simple. When you call evaluate, it creates a new expression tokenizer, which is equal to the expression you pass. And then we create a new expression tokenized parser, which calls the tokenize function. This function takes in the expression that you want to tokenize and splits it into an array containing numbers, parentheses, and operations. In order to demo this, instead of doing this, we can simply do this manually. So we can do expression tokenizer is equal to a new expression tokenizer. And for example, let's do the example something that we previously had. And then we can system.out tokenizer.tokenize. As you can see, this will give us a nice array list containing the string values of the operation, the number minus 2, and parentheses are grouped into one to be parsed by the next step, which is the tokenized expression parser, which takes in tokenizer.tokenize. And this class has one method, parse, which returns a node. Because the way this works is a tree. A tree is made out of nodes which have a token assigned to them, as well as optional left and right nodes. And the way this whole system works is the token has a function called execute and a double called value. This value is then to be updated in the execute function. So in operation token, which performs an operation, if the left and right nodes are not null, then we execute them, meaning if we have a tree with, say, even another operation token on the left, we will execute that one, and so on and so forth. And then we get the values of the two nodes. And then we calculate the result and set the value to the result. The number token, which just stores a number, has no execute and instead is just a record which automatically stores the double value in it. And the tree itself is made here. So we would then store the tree as a node is equal to parser.parse. We then execute the tree.get token.execute, tree.get left, and tree.get right. And then our answer will be stored in the tree.get token.value. So this expression will evaluate to negative that. A simpler one, which will give us 4, evaluates to 4. So I'm gonna tell you how this works. So we start with just creating the result node, and we have a regex for detecting operations, and then we loop through the tokenized expression list. We get the token, and if we only pass one token, for example, if we just have one, for example, it will evaluate to just one, which is returns. Next, we check if the current character we are on is a parentheses. In this case, 1 plus 1 times 2. The first character is a parenthesis. So, because this is true, we call the evaluate parentheses function, which takes in the index of the parenthesis, and calls the parse parentheses function, which basically just removes the two brackets from it and calls this class again. So it basically just evaluates the parentheses and returns the value. And then we remove the parentheses from the array list. So if here we run this, we have the parentheses, we evaluate them, we remove them from the list, and add the value back. So we have 2, and then we're just left with 2 times 2. So we go back up here, and now we check, then we go to the next character, which would be at this point 2, and then we go to multiplication. Because this matches the operation regex, we find the operation, which just finds the operation from this enum, which contains a operation priority for order of operations and the actual operation that we look by. Next, we try, because this can throw an index out of bounds exception, we try and, first of all, we check for more parentheses. If either of one of the operands are parentheses, we evaluate them. If it's not, then we check the next operation in the sequence. This is where the index out of bounds exception can be thrown, because there might not be one, but that's fine, because if there's not, then we just skip this whole part and skip the next part. But if there is, we basically just do the same thing we do with the operations, where we evaluate the greater one, remove it from the list, and place in the new one, and then we just continue on. Then we find the operand 1 and 2, and then we just create a, if the result is null, so if there is no tree existing already, we just create a new tree from scratch, like this. But if there already is a tree, we save the current tree into the variable called temp result, and return a new tree with the operation token, the previous tree on the left, and the operand 2 on the right. And then we just return that result. And that is how my simple parser works. If you would want, it is available for download on GitHub. It is simply fluffster4/Java expression parser, and you can download it using Maven, Gradle, or just the jar file if you want. As an example of usage of this library, I created a simple calculator application which uses JavaFX and this library. And as you can see, here we are evaluating the expression using this very simple syntax. And when we run this, we get this very simple calculator where you can say do 5 plus 3 times 2, which using order of operations, you would do 3 times 2, which is 6, and then 5 plus 6, which is equal to 11. And as you can see, that evaluates to 11. You can then do 11 minus 6 to get back to 5. And yeah, you could basically just do whatever you want. You can multiply it by this, and as you can see, it even does scientific notation. So yeah.